Okay. Hi everyone. Thank you all for coming in. If I'm not audible at the back, please let me know. The recording that's actually meant just for the video, and if I'm not audible at any point, just let me know about that. So again, thank you all for coming in. Giving this short talk about the theory of design that I learned in an architectural setting. I'm an architect myself by my undergrad training, and the previous talk actually set up like a good background for me. The idea of a designer, it's actually so vague. It's like coming in from so many different perspectives. You could be designer, but personally, at the end of it, the way I take it is like problem solving. If you're solving problems, you're doing design, and that's something that's been a core part of architectural ethos like from the beginning. The term itself, architect, it's like compound of two words, architect meaning like master builder, and this is like way back. Sometimes like there was some construction to be done, and like who manages it? Like this guy, he's the master builder, so he's an architect, which like slowly transformed, and now we have this like very well documented industry and like a profession called architecture. So given that background, that's how I started in. But right now, how I work is I work as a computational designer, and which essentially is using computational processes in any means for architectural design, or could be anything. So this is a classic example I use for explaining the idea of how different computational processes come into the world of architectural engineering and construction. It's a public building. I'm not sure if I can call it a building. It's like a public monument that's recently opened in New York. Was done by a British architect, Thomas Heatherwick, and the engineering was done with Thornton Tomasetti and AKT2, who are from New York and London. So the computational parts comes in like different parts and processes about this, where you can see in the design process they use sort of an algorithmic approach to come up with the design in terms of 3D geometry, passes it on to the engineers to analyze it, to assess it, and from there it goes to the next step where in the design process itself you mark out how the construction, how the certain different members that you can see they're going to be, and they go back on site to be reassembled sort of like a jigsaw puzzle way. So it goes full length, like from design to being engineered to the fabrication, and computation is like an aid that you use in the process. Similar approaches have been used for fashion, where they've come up with like using different computational means and takes. Like, I'm not a personal expert about this. It's a project I found online done by Fab Textiles, where they were using computational processes to come up with different designs and materials. Similarly for architecture, or sorry, for product design or furniture, where you use the approach. The idea is to have a product that's usable by people. How you approach is like your own idea of what design is. And coming from this background, I was looking at the whole field of architecture, and the industry or like the profession being so old has a big volume of work about the theories that come up with design. And a lot of the discussions that we do in today's practice as a computational architect or any architect per se starts at a lot of abstract level of thinking, and that was really interesting to me, and that's how I got started in this, where a lot of common problems, be it like experiential, be it physical, be it technical, were having repetitive solutions and coming back, referring back to the same methods and techniques. So through this talk, I'm going to go through a bunch of different examples of how the problem has come up and like been resolved in different ways. And so it's going to be a collection of different things. So there'll be a lot of context switching involved. So just heads up. The first one that I'm starting off with is this book by Christopher Alexander, Sarah Ishikawa, and Murray Silverstein called The Pattern Language. This idea has been used across in a lot of industries. Like it's also very popular in the software industry, where like there's this book, The 5 Designs. I'm blanking on the name, where you have common. So what the book does is it creates a new language called a pattern language, and patterns describe the problem and offer a solution. So common problems common approaches, encode that as a pattern. So it's reusable in different aspects, but it's not like specific, and this way like the abstraction works to separate yourself from the core issue, think about it at a higher level, and then reimagine how you can apply it at different scale, different uses. This is the whole book is a big collection of patterns. I'm not even sure how many, like I think it goes 200 plus. The book came out in 77 and it was a collection of his work over a period of 10, 12 years before that. And this is just one of the examples that I'm using. And the context which he's describing this problem is in looking at the city is not a tree, but it's more like a connected graph sort of thing, where like if you look at a city, a very top-down approach, like there are big districts, and then you narrow it down, you come down to the neighborhood, and like that sets up a hierarchy. This is actually trying to describe that issue in a slightly different way, where the point he's making is a city is comprised of different units, and each set of each unit, which he's calling a set, and a set is a collection of elements which interact together, relate together in some way, and they make a whole unit. It'll make more sense when the example comes up. And organizations of these sets form the experience of a city and how different cities are. And you might be different cultures, different location, different scale, different sizes, but it's the similar nature of breaking down, trying to understand a city. So this is an example. Like imagine a corner store where there's the street, the footpath. Since this is all architectural, a lot of physical discussions, and it's all the common elements that you would find in any normal city. And he's explaining the way the city comes into existence, the nature of the people, the identity, the location, is how these interactions work, and they agglomerate together to form a comprehensive definition or identity for the city. To get this point through, for this example where he's talking about just a corner store, we're going to go through the next slide looking at the same description across different cultures and different places. So a place, I'm familiar, like this is somewhere in America. Same thing described in another place. I'm not exactly sure where these locations are, but you can identify like the similar typologies. But what changes is the scale, the busyness, the different aspects, but it's the same interactions happening across different locations, different cultures, different geographies. And that's kind of how this book is talking about, like describing problems at that higher level and then looking at it individually. Yep. So that was one of the first examples in my collection of excerpts. The second one is a classic book I've seen being used to introduce architectural design for first-year grads across a lot of places that I've met. Usually in like the beginning years of architecture, where you're trying to explain to a kid how to go about architecturing. The book was done by Francis D.K. Ching, and it's a book called Form, Space, and Order. So trying to explain to a kid like go make a building is kind of a difficult problem. So they try to break it down into simple elements. And at the beginning itself, it's more mathematical, I would say, where he's just talking about abstract spaces, points, more like geometrical stuff. But I like the approach how he took to come up with the design, where break it down into these simple elements, explain how their interaction works. At this point, we are still thinking very abstract. It's not really a building that we are necessarily talking about. And explain how they collect together, they interact with each other, how they form together. And it's starting to think of these elements as tools that you can use in your design process. At the same time, what we are doing is like thinking about it in 2D because it's easy to comprehend that. Designing in 2D and thinking in 3D. So one is like what you put on paper and what's in your head. And the abstraction that architects always use is meant to convey to the client, to the contractor, to yourself, to your team. And the book has a nice way of approaching this. It progresses to like using these elements and starts imparting meaning to them. a similar element, like in this example, a plane, whether it's placed vertically, horizontally, or sideways, imparts different meanings to the space. And then you start thinking about then how you can use them in your design process to maybe design a certain corridor a certain way, or like design a certain corner of a room or a building. And this is a good analogy about how he, in a way, is like justifying the origins of these meanings, because these are like raw geometry, but imparting meaning to them is kind of like things that we've started associating with them more like evolutionarily, I would say. And this is just touching on the issue of form versus function, which is a big debate in architecture. It's like a timeless debate where the discussion goes like the architect is making a form, has to look beautiful, if you can call it that, but also at the same time has to be functional. So what takes precedence in such a discussion? And I think I hear similar discussions in like the dev world, I would say, where you're thinking about like, oh, beautiful is one thing and like functionality is one thing, but I don't know, it's an open discussion, I would say. So that with this is gonna be like the last example that I go through, and I'm sure there are tons more. So this is looking at the city at a larger scale and trying to understand why cities come around to be how they be. I'm going to run through a few examples. What this image is showing is what's called a figure ground plan, where you take the whole layout of the city and just block out the building footprints and put it on the map to scale. That's New York, Tokyo, Brazil, Sao Paulo, DC, Barcelona, Singapore, Istanbul. So with these collection of images, you can see they come from different locations, different places, different cultures. But if I'd like to say like a common pattern that I see in them is like how orthogonal they are, like how everything is square, not necessarily to the whole layout, but the individual massing of the buildings or the place, it just ends up being rectangular. And this is more like a post analysis of the situation of how cities end up being like rectangular. So coming to approach that from a idea point of view, why urban masses end up being, there are a lot of theories about why a square grid is good. A lot of it comes from like theory of how cities came into existence, how they to make it secure, how they were good for like militaristic purposes. But this is a more higher level analysis, I would say, where we start thinking about like space in terms of units, because the idea of city is like everyone living together close nearby and best optimal use of the space itself. To do that, you start like laying out how your city is going to be, and the most convenient pattern to work around with is what's repeatable, does not waste space in between, and it's like more consistent in size. So I think there are just three of these shapes which actually do that. Like if you lay them out on a sheet or like individual pieces of them, they're not going to leave any void space in between, and the sides of each member of them, they are the same. So that's like difficult to ascertain, but like useful if you think of it like city blocks or construction units. Having standard sizes is good, like makes a lot of things easier. By that logic, like considering these three fit, there are still more dimensions for understanding why a square grid wins out in some sense. So the parameters that we are assessing it is in like these 5 aspects. One is like if you have a block, what's the future possible direction of growth? A square gives you 3 sides of growth, a triangle would give you 2, and a hexagon would give 5. So in this sense, like the hexagon makes more sense, like it's more versatile, but there are other points that it's losing on, and I'll rush through them quickly. Understanding negative spaces in between. So negative spaces are like these red corners that you see in here, like tight corners in a room. That's not very convenient to use in because it just ends up being weird and by the nature of it. Squares don't end up with any negative problems. Like it's all 90, so it's all good. These things individually, the triangles individually have like 3 zones of the negative usage. If you put them, like if you start stacking them, you can avoid one of them, but you still end up with two of them. Hexagons, the inner corners that you see marked here in red, like they are not necessarily like claustrophobic, inconvenient, but they more like create these weird angles that's difficult to design things to put inside, or like design things to forms that acute angle on the inside. Then looking at the angles that we have, a square just has one internal angle. So you have a piece of table, shove it in the corner, can go in any corner. If you start thinking of that for other shapes, like if to start having different kinds of tables. The fourth point, that's like very interesting. That's like when you have start groupings of these shapes for whatever reasons and purposes. That's the whole idea of modularity and flexibility. With a square, like if you start picking like different units to combine together, you have like 53 combinations, 68 combinations, and one combination with these three shapes respectively. Where again in this case, like the triangle maybe wins out, but over the analysis of it across these 5 points, that's when like the square starts winning. And the creation of interior angles. That's imagine like putting up a partition in between, like a false wall in between that's parallel to one of the edges. You still have a consistent angles in the square and not so consistent in the other shapes. But again, this is more like a post-analysis of the theory rather than why we start building as a rectangular and analyzing it at more at urban scale. So in thinking of it in terms of massing instead of individual rooms and per se. And I think, yeah, that's it. So those were my few collections about these excerpts. We still have 2 minutes approx for questions, so feel free to shout out. Hey.
How do you understand the slide emergent charts? Previous,
This one?
last column with the
The last column?
no, the one before. Sorry.
Second one. Okay. So I'm going to go outside the video slide. So this is 1 unit, but this is also 1 unit. This is 1 unit. So put them next to each other and start grouping them, because imagine a room or a city block and you want to expand it. So you can have different combinations. Sure.
Yep. In this slide, destination shapes, did you also take into account the shapes of the roadway between the that sense, this is where
True. I see what you're saying, but it was like I wasn't looking at it that sense, because it's more like roads can be collapsed into one. Like if a property developer wants to buy more properties and start thinking around that, then it's not really a problem.
Any other questions? Yep.
Since we are talking about city design with destination, I read a paper about strong destination on fairly regular cities create a crystal shape of it, which concentrates it at the center of the city. Is this taken into account for some designs?
I'm sorry, I didn't fully get the question. Could you speak a little louder?
When cities are extremely regular, it creates a crystal shape for physics analysis. It really fits the center of the city compared to more random shapes that spread the heat around.
Mm.
Is there a model for this or something?
No, but
In the destination?
that's a really interesting analysis. I don't know about it, and I haven't come across that. But the whole, like in urban design schools, like there's a discussion of heat island effect, but that's different. That's more like materials and how they interact with the built mass. But that's a interesting point that I'm going to look up.
Okay. If there's like a very concise question, because we need to leave a lot of people in, you've got 30 seconds. As a challenge. No? Okay.
So thank you very much.
Thank you.